Good morning, everyone. Welcome to our big data lecture today. Last week, we continued with parallelism, and we saw how we can easily create threads in Python, most easily with a thread pool. If we have lots of parallel work that needs to be done, this thread pool encapsulates the work for us very well. And then we saw how we can create our own threads, and we actually wondered, we had something like a very large counter, like 50 or 500 million, and saw it takes our computer maybe a few seconds to count down to 0. And we wondered if we can speed that up by halving that count and then running 2 threads. But we noticed this had not led to any actual speed up. We wondered why, because of the global interpreter lock, which tries to prevent any kind of lock issues, deadlocks, which you need in order to prevent leaked memory. But locks typically lead to deadlocks and lots of other issues. So the global interpreter lock is a lock on the global level of the interpreter in order to prevent leaked memory from happening. Unfortunately, that does not allow us to use threads in parallel. So our thread pool from before, it actually doesn't use threads. It's from the multi-processing library, and you can take a look how it's implemented. Certainly not with threads, rather with processes, because the global interpreter lock does not allow threads in Python to run in parallel. That concerns the CPython implementation. There may be others. We've discussed some benefits of the global interpreter lock, and we looked how we can actually do multi or parallel work by using multi-processes, multiple processes that run in parallel rather than threads. And currently, Python is undergoing some transitions so that the global interpreter lock is slowly being phased out step by step. But certainly in the early days, it made sense to build the global interpreter lock this way, but computing has changed, and we need parallelism to work on ever larger data sets. What I said all concerns the CPython implementation. We looked briefly at a few others, how they handle the global interpreter lock. We saw a few more best practices for parallelism and briefly looked into asynchronous programming. And then we started looking into big data architectures, which we need in order to handle our large amounts of data, in order to contrast the approaches we're just discussing today to traditional relational database management systems. We just did a very brief revision about the key pieces of a relational database management system. In particular, we looked at ACID, a set of important guarantees, which we are going to contrast today to other properties in a different setting. Did anyone try out the SQL murder mystery? So it's just for your revision, in case you want to improve your SQL skills, I can highly recommend this. And then we looked into distributed systems and in cloud computing as one derivation or one concrete variation of distributed systems. And then I told you writing parallel code is tricky. And there are a lot of smart coders who don't know very well how to write parallel code that works. And Google discovered that more than 20 years ago as well. Despite having lots of super smart coders, they struggled with building parallel code. So what Google introduced is an abstraction called MapReduce. It's a programming model. And that programming model allows to parallelize a lot of tasks without actually thinking about threads and synchronization, but rather the actual computational problem will be rethought into a map and reduce phase, and then a system is being used which runs these threads and takes care of all of this in the background. But all you need to do is you need to define your mapping and reducing functions. This is probably one of the most influential papers in computer science ever, this MapReduce paper. And MapReduce nowadays is still used in some other variations. Obviously, a lot has happened in those 20 years, but that idea of how to split this computational task still holds true today. Anyone had a look at the paper? Okay. What do you think about that paper? Readable? Was it easy or tough? Do you like it or not?
It's a relatively simple idea, MapReduce, but it becomes more and more complex as you read the paper.
Yes, that's true. It starts with a relatively simple approach and becomes more and more complex. I like that paper. So what does it do? We're not discussing it in detail now. You're expected to read it, and some of you have read it. It introduces the programming model so that you have a mapping and a reducing function, or you write these functions, and we'll look at a concrete example, and then this probably becomes more obvious. And you don't need to, when you use such a system like the one that Google built, and there are lots of open source variations like Hadoop or Spark, which slightly changed that approach. You don't need to worry about the parallelization too much. Rather, this is done by the platform for you. You just write your functions, and then how it's run on which system or how it's distributed and how it's synchronized is not your problem. So you can actually have highly parallel code or highly parallel, you can solve a problem in a highly parallel way without worrying too much about the actual parallelization. Imagine we have now, so this is the general overview, but we will look at it from a concrete problem. Imagine I have a super large text file, maybe terabytes. And what I want to do is I want to do a word count. Concretely, I want to count how often each word appears in that file. So what I want as an output is a dictionary. And the dictionary would have a key, which is the word, and the value is the count. But now I have this super large file, maybe terabytes, petabytes large, and processing it sequentially will quite take some time on my local machine. So rather, I want this in a distributed way and parallel way without worrying how to write that code. So I can think about two phases. I can think about a mapping phase and a reduce phase. And then initially, I would take this very large file and I would split it into a certain number of chunks. Can be 5, can be 100, whatever. And then I have these map workers, and the mapping essentially will, for this use case, do a word count and return a dictionary for each of these splits. So I have a worker on this split, some worker works on split 1, some worker on split 2, and I have a certain number of workers. Maybe once a worker has finished, it will work on a different split. Well, I'll split it, and for each split, what I will get is a dictionary for that split, which is my key values. But then I have various of these dictionaries, each coming from one of the maps. And then in the reduce phase, all of this is combined. So two dictionaries are merged, and I have one big dictionary as the output. That's the idea of MapReduce applied here to the word counting, which is also as an example in here. But when you read the paper, there are more examples what you can use it for. Count the URL access frequency, reverse web link graph, term vector per host. And this proved to be quite an influential paper because the approach that Google went suddenly allowed a lot of coders to have highly parallel code without having to think about threads and synchronization and locks, but rather just write these functions and then pass it to the MapReduce engine, which would run it and take care. Obviously, building that engine was tricky, but obviously Google had or has smart people who know about parallelization, and they rather spent their work on building that engine, and then everyone could use it. And there are lots of open source alternatives like Hadoop, Spark. Spark follows a slightly different approach, but it's still more or less the same idea. Feel free to read that paper. It also has some implementation notes and some challenges they faced. think it's a very good paper and starts easy, becomes more complex, but overall is quite readable. So this was the MapReduce paper, which you can read again on the weekend in case you have not. Now I want to discuss something with you that is called a cap theorem. When it comes to a distributed system, let's think about, we have a very large social network, for example. And it's just impossible to have one node that can process all the requests from the users, because the node would just be too slow. So we want multiple nodes, so our social network is still usable in an available amount of time. That would mean availability, that we can actually access and use this, and we don't need to wait forever. But now we make changes to the social network. Like I add a friend, I send some messages, maybe delete some friends, and I run some of these changes maybe all on the same node. But if other users access other nodes, they may not necessarily directly see all of these changes. Maybe something you have noticed, if you click somewhere, say on LinkedIn or Facebook, and you click a like and you refresh, sometimes you don't see this anymore, what you have done immediately. Have you noticed that issue? And this has to do with the cap theorem, because there are three guarantees. Availability means the node is actually usable, available. Consistency means when you make a change to one node, it would be available on all the nodes. And partition tolerance means your system actually still works well, even if you have an arbitrary number of messages being dropped. Messages here means communication among the nodes because of some network issues. And the ideal distributed system, you would think, well, we want it available, we want it consistent, and even if messages get lost, so the partition tolerance, we still want it to work. This would be our ideal distributed system. The problem is such a system is not possible to exist. There's a paper for this and a proof that a distributed system cannot simultaneously provide more than two of these guarantees. And when you use, for example, a social network like LinkedIn or Facebook, they rather want it available and they still want the system to work despite there may be some network issues, but they sacrifice consistency. And that's why it happens, maybe you send out a message in a social network, you click like, and someone else will not immediately see this. Or even if you refresh, you may not see the change and you need to refresh a few times until it's there. That's a consequence of the cap theorem. So it's not a bug in Facebook or LinkedIn. Rather, what they say is, well, we want the system to be available. Lots of people use it and they send out messages, read the news feed. And even if there are messages lost among the nodes, we still want it to work, because the worst thing would be with a social network like LinkedIn that you need to wait in order to see some update. But it's not immediately consistent. So maybe some of the changes you make are available only a few seconds later or a minute later, but that's not too bad. If you click a like, no one cares if it appears 5 seconds later or earlier in the other nodes. So they picked these two guarantees, availability and partition tolerance. Would you pick which guarantees would you pick if you run a very large bank and you want to allow payments in a network? Why consistency? Yeah. Exactly. So or we don't want people to make the same payment many times and spend more than they actually can spend in the account. So such a bank would definitely pick consistency, and then you can pick one of the other two. Here, maybe partition tolerance or availability would depend a bit on the system and which guarantees you want, but definitely consistency, because you don't want the same payment to be made many times and people spend more than they're actually able to spend. So consistency would be in such a bank setting far more important than in a social network. This was at least the rough idea of the CAP theorem. The CAP theorem sounds great in theory, and it has obviously impact on real-world problems. But it also implies if there is network partition, you would need to pick between consistency and availability. But if you don't have network failure, so if partition of the network is not an issue, then you can, in fact, choose both consistency and availability. And when you look at companies like Google, obviously they have huge distributed systems with lots of data. They're doing quite a few tricks in order to make these guarantees work as good as possible. Last year, we had a speaker from Google here in the class as a guest speaker, and I think he talked about some issues around the CAP theorem for Google. You can find the recording on YouTube in last year recordings of the course, and we'll have the same speaker this year. Let's see if he will also speak again about the CAP theorem, or if he will speak about something else. But it's something that keeps these big companies like Google, Facebook, and so forth quite busy because they still want the system, obviously, to be as consistent as possible, but largely available, and keep network errors to the absolute minimum. But sometimes there are some. So maybe take a look at the recording from last year, and we'll have Ramon here as a speaker, but probably he will join online again sometime next month. So actually, we can now wonder about ACID and the CAP theorem. We saw ACID last week as a revision. Do you remember again what ACID stands for in relational database management systems? We discussed it last week. Who remembers what ACID means? Louder?
Availability, consistency, isolation, and
atomicity is the A, then consistency, isolation, and durability. Very important guarantees for relational database management systems. And now, when you have a relational database management system, you cannot just have one node. If you want, you can have also multiple nodes, just in order to scale it more to very large amounts of data. Maybe you have worked with a database management system and you were able to create multiple partitions. Has anyone ever done this? Certainly something you can do in the settings to increase, for example, or to make it faster, to speed up. But because you have these very, very strong guarantees in ACID, definitely such a system needs to favor consistency over availability, because we saw ACID strong guarantees, atomicity, consistency, isolation, and durability. So why would you actually have such multiple nodes in a database management system? Maybe because you just cannot store it on a single node. Maybe the database is just too big to store it on one node, so you need multiple nodes, and you would split the data among these nodes. But such a system always would favor consistency over availability, because ACID is a very strong guarantee, and that's the reason why relational database management systems are so successful and why we will still have them probably in 30 years from now in some form or another. Now, it turns out in distributed systems, especially now in this big data world, social networks, and so forth, there is a different set of guarantees. First of all, the kind of database systems I want to refer to now are often referred to as NoSQL. Who of you has ever heard that term, NoSQL? Good, some. It's some term that became popular maybe some 15 years ago or something like this. What does NoSQL mean? This refers to a huge set of different database systems, and you would think, well, they don't use SQL. You use some other language to query them. That's partially true, but it turns out there are some NoSQL databases that use something like SQL or something that looks almost like SQL. So what does NoSQL mean? It does not necessarily mean that they don't use SQL, but rather maybe not only SQL. So these systems often come with different guarantees. Such kind of systems have already existed since the late 1960s, actually, but this term NoSQL only came up some 15 years ago. And this was often triggered by the needs of Web 2.0 companies. This is also some term that came up some 15 years ago. So web companies that deal with very large amounts of data, and they want to be available very quickly. And this term NoSQL is just a huge umbrella term for a lot of different things. That's why, to me, it doesn't really mean it does not mean not SQL, but rather not only SQL, to describe a huge set of different databases with lots of different architectures. Some may even use SQL or some query, but they come with different guarantees. And a set of guarantees that is quite common for a lot of these systems is not ACID, it's called base. What does base stand for? It comes with some very relaxed requirements. Base stands for basically available, soft state, eventually consistent. Something quite fussy compared to ACID. But what does it do? Let's start with the soft state. We have states, but they are not fully consistent because we want the system to be available as much as possible. So we sacrifice consistency. So we deal with soft states, which are not always fully consistent. But we say the system would become eventually consistent. We don't give any guarantees how quickly, but we say over time, as we wait and the nodes synchronize, it will become eventually consistent, not immediately. But we increase availability to the maximum degree possible, and we say it's basically available, so that basic read and write operations are available as much as possible. And we use all the nodes of the system, but there are no consistency guarantees because it's a soft state and eventually consistent. So pretty much the exact opposite to ACID. Because for ACID, we said we isolate all the changes, we always have consistent states, and once we have finished a change, it's definitely durable and available. Where available means not as the system, but the change. Once we query, that change is there, it's durable. And base is just the exact opposite because we deal with soft states that are at some point consistent, and it's basically available. And this kind of stuff has become popular in the last 15 years. And without these kind of technologies, we wouldn't have all these social networks or a lot of big data applications. Because if we ran all of this purely on relational database management systems, it would just be too slow given the amount of data and the users and the changes. So I'm not against the relational databases. They are super important and they will still exist for many years to come. But they're not the only option. So when you design a distributed system, it largely depends on your use case, what you would pick, or which open source implementation you would use when you build a system. And ACID is important, but not necessarily the right thing for all your problems. So remember what ACID stands for and base, which is just the exact opposite. And a lot of systems in this NoSQL world, they follow this base philosophy and they choose availability over consistency. So now we've looked at different architectures and different guarantees. Now, when we have big amounts of data, we also need to be able to run our computations very efficiently. And since most of you study here in the framework of an AI program, I want to talk a little bit about efficient training of neural networks, for example. Nowadays, GPUs are super popular to train neural networks. And there's a reason for that. So I've been following GPUs and how to use them for training neural networks for quite more than 10 years. So I was probably one of the early adopters more than 10 years ago, because what I saw, training a neural network on a CPU does not work too well. Does anyone of you know why GPUs have become so popular for training neural networks? Why the GPUs are now so helpful? Why do they better than CPUs? Mm-hmm. Okay. Yeah, that's high level. Maybe some more details, like how does the GPU exactly support parallel work? Yes.
Very basic operations like addition, multiplication,
Mm-hmm.
sometimes not, but they're basic. And it's very easy to compute, make these computations. But the problem with CPUs is that they only have like so many cores,
Mm-hmm.
whereas GPU has tens of thousands. And if you parallelize well, then every core of the GPU can do, say, one computation at a time.
Okay.
This would be like tens of thousands of times faster than CPU would.
Perfect. I agree very much with this, and I will outline it a bit. So why are GPUs so popular now, and why is the NVIDIA stock, ever growing? I know it dropped now in the last few days, but it will definitely go up again. So when I was a teenager, GPUs were used purely for playing video games. And how do you represent computer graphics? How do you do computations in computer graphics when you have all these pixels or these objects and you move them around? All of this can be described in terms of linear algebra. So you have your object and you have a matrix for a translation or a rotation. And this is how computer graphics has been done for many decades. And then GPUs were built in order to support that you have linear algebra operations, largely matrix additions, matrix multiplications, or multiplying vectors with matrices and so forth. And this helped to speed up computer graphics a lot in, say, as of the 1980s, 1990s. The way AI models were trained was still purely on CPUs, but then when was it? About 15 years ago, some people rethought how to train neural networks. And rather than writing, a lot of loops in the training phase and adding elements together and multiplying, this was rethought that maybe you can do the operations in a neural network, that you can express them as linear algebra operations. So rather than adding elements together, rather you add vectors or you multiply matrices. And then it was noticed, if you do that, you can run the training of a neural network on a GPU. And this became more and more popular. It's something I said I adopted more than 10 years ago. The only problem was writing code for a GPU. It's quite different than writing code for a CPU. And it depends on the vendor or the manufacturer of your graphics card. So for NVIDIA, you have CUDA. For the other vendors, you have different libraries. So you need to learn how to write that code. And it's often very low-level code, in fact. And that made it super difficult to start using GPUs for training neural networks. But then maybe some 12 or 13 years ago, some kind of libraries came up. They had a high-level Python interface, and they allowed you to use that. And in the back end, all of this was compiled to CUDA code. CUDA just as a synonym also for the other vendors. And one that started coming up 12 or 13 years ago was Theano. Theano is something like NumPy, but it doesn't run, or it runs on your CPU, but you can also change a flag that all what you're doing is compiled into CUDA code and you can run it on a GPU. This was the first level to speed this up, proved to be very effective. And then over time, more and more libraries for neural networks came up to do exactly that. So they use something like Theano, and on top of that, they built some more features for neural networks. There was, for example, a library very popular 10 years ago. It was called Lasagne, inspired by you have different layers that you add together. And then TensorFlow came up. I still remember this. TensorFlow was a big change. It came out, I think, in late 2015, in which you simply had a much better library to build neural networks. It was still far more low level than it's today, and you could map it to a GPU. And something I noticed was when I did my master's, we could use a GPU there in the lab, and then I switched to a different university for my PhD studies. And my advisor, I told him I had used a GPU for training neural networks, and he wanted me to get one too for the lab. So that was my task in the beginning of my PhD studies. And it was pretty cool. So my PhD advisor, he just got his own research group. So there was some funding available. And we bought a GPU that cost $5,000. At that time, we paid $5,000. A Tesla K80 that was popular 10 years ago. And that thing had something like 5,000 cores. And the GPU is like this, that long. So more than 50 centimeters long. But if you are into gaming, this will not help you because these modern GPUs, they even don't have a video output. So they're purely for scientific work. And then we needed to build some other stuff around it, and we were at around $10,000. And I did my PhD in Luxembourg, and it turned out I was the first one in the whole country of Luxembourg who ordered this kind of stuff from the US. And in the US, they're quite strict about export regulations and dual use items because GPUs are not allowed to be sold to certain countries. And in the US, there's an agency to control this kind of stuff. It's the US Bureau of Industry Security or something like this. You can look up what the name is. They are specialized on such stuff, export regulations. And they got a list of who bought what in the US. And they actually were curious because I was the first one who ordered this stuff in Luxembourg, what we were using for. And they flew in from Washington, D.C. to Luxembourg just to check our server. So we made an appointment, or they made an appointment with us, and they flew in, like two agents. You imagine it looked like FBI agents. And they came in, and they just wanted to see the server, and were curious that it was still there and not sold to Iran or North Korea. And it turned out they had even no clue what a GPU was. They just knew it could be dangerous, and they wanted to see we still had it in the lab. So this was one of my experiences as an early adopter. Nowadays, everyone has GPUs, and the export regulation is less. But 10 years ago, this was still quite strict. And I asked them what happened if we did not make the appointment with them, if we did not show them our data center. Then they said, well, then you're never going to travel to the US again. So they're quite strict with this export regulation stuff. But we just showed them the server, which took 2 minutes, and then we had coffee for 1 hour. And they said they actually enjoyed flying to Luxembourg before they had been to, I don't know, Libya or other places. So I think they preferred Luxembourg very much. Yeah, so this was my story, my experience as an early adopter. And nowadays we have obviously much bigger GPUs. It's a big business for NVIDIA and others, and with ever more specialized cores. But there's also a lot of misunderstanding how this kind of stuff works. Like also maybe 10 years ago, one person told me, and this is no joke, but I'm putting the quote here. That person said, CPUs have no future. Their future belongs to GPUs. What do you think about that statement? Like in general, for any kind of computational task. So you say we still need CPUs. And I fully agree. I think for this, and we also have someone in the chat, one person says GPU are faster, but CPUs are smarter. Okay. And one person says some tasks do not need that level of parallelism. So a CPU nowadays, thanks for all these inputs. Anyone here wants to say something too? Because we're already one student. Anyone? Okay. Yes, but that's true. But there are also cheap GPUs and super expensive server CPUs. So there's a huge variance in the pricing. But they work totally differently. That's why I totally disagree with the statement here. So a CPU, one person says something like GPUs are faster, but CPUs are smarter. This is actually a very interesting sentence that one student wrote here in the chat. So a CPU is a phenomenal piece of hardware because it can do far more than, plus and minus and divisions. It can execute very, very simple instructions like adding two numbers, but also extremely complex operations on a huge array of data, for example, and some sophisticated operations. If you take a look into the data sheet of modern CPUs, it's probably hundreds of pages long, but all the instruction set. And the good thing is, if you write code for a CPU, it's usually quite easy to code. You don't need to use assembly language. You can if you wish, but you can also use C or C++, Java, whatever. But let's maybe leave out Java and Python because there's an interpreter in between. So we take compiled languages like C or C++. And it turns out, even if you write very poor code, your CPU can still run it much faster than you thought. Are you aware of this? So the CPU is really smart. Even if you write really bad code, it still runs fast. We're not talking about Python or Java. There's an interpreter in between. So what does a modern CPU do? It can, for example, do out-of-order execution. So when you have your assembly code, so you break down, you compile your C code, and eventually what you see is assembly code. The code is not executed in that order in your CPU. Something we call out-of-order execution, because maybe sometimes some command or some instructions, they take longer than others. So they're sometimes resorted or even run to some degree in parallel just to speed up your code. So if your code was written in a bad way, the CPU can try to improve it. And then this is all linear code, but you also have non-linearities in your code, like if-elses, branches, for example, or loops. But loops, eventually, you have a jump and then a condition whether you jump again or not in the code. Now, when you do this out-of-order execution, it may go totally wrong, because if you execute some later lines, but then actually you notice you should have taken a different branch, that wouldn't work well. So what a modern CPU can do as well is branch prediction. When it looks ahead and tries to execute some statements in advance, it will already use some sophisticated logic trying to figure out which of the conditions is most likely true and not. It's not necessarily true. The system may guess wrong, and then there's a rollback to rollback operations that were already carried out. Did you see such stuff in your operating systems class? Was this mentioned or not? Maybe if you've seen this kind of stuff before, raise your hand. Okay, no. So this is what modern CPUs do. And it turns out when you look at the actual CPU nowadays, 50% of the CPU is not the actual computation, but 50% of the CPU of the chip is largely this kind of stuff, branch prediction, out-of-order execution. So this is nowadays about 50% of the chip. But it really helps. And if you have really poor code, it can still run surprisingly fast. But a CPU also has limitations. We have a very limited degree of parallelism. We have a bit of parallelism. Things, for example, SIMD. SIMD stands for single instruction, multiple data. So we apply the same instruction on a whole array of data at the same time. We have a few cores, and in the cores, we have pipelines. So with pipelines, we can get a little bit of parallelism, but overall, parallelism is limited. So this is the setting of a CPU. And the GPU is pretty much the exact opposite. A GPU has a very high degree of parallelism, but using that parallelism is tricky because we need to learn how to use some specialized library like CUDA or whatever. And most GPUs, they don't have much of this other stuff. Like they cannot really optimize inefficient code well. So most GPUs don't have much or none at all, like branch prediction, out of order execution. And mainly we have a lot of cores, maybe even thousands of cores, but they can only do very, very simple stuff like additions, multiplications, and so forth. So it's actually quite the opposite. And I don't think that one is better than the other. It depends on your use case. So this statement here that CPUs would have no future, the future would belong to GPUs, certainly not true. It depends largely on your use case. There are also some interesting hybrid architectures that try to merge both, like Apple is doing, for example. So it's something quite an interesting time. But what I see is in GPUs, the number of transistors doubling, or time it takes until the number of transistors on a chip double is currently much faster for GPUs than for CPUs. And there we see huge improvements and obviously a lot of investments in the R&D, because NVIDIA and the competitors are obviously very excited about this AI reality that we're in now and that people need high-end GPUs. But there are also totally other approaches to actually train neural networks. So yeah, you have GPUs, but you can also have these tensor cores and stuff. But there are also, for example, FPGAs. What is an FPGA? Anyone has ever come across FPGAs, ever used them? Okay, what have you used them for?
Used them myself, but I came across them in context of edge devices.
Mm-hmm. Anyone else? So I have to say, when I studied computer science, the computer engineering part, so how hardware works, was actually a much bigger focus of the degree program than it's here in our degree programs, which is sometimes a little bit sad. But instead, we focus now on AI and other things. But I had, I think, 3 modules on computer engineering, so on computer architecture, hardware, which was, I think, a very good basis. And we also used FPGAs in the lab. So what is an FPGA? All the chips we looked at so far, both CPUs, GPUs, they are so-called ASICs, application-specific integrated circuits. So a custom-made circuit for a specific task. You can have not just GPUs and CPUs, but maybe even much smaller, simpler embedded chips. They're all application-specific integrated circuits. And if you want them to do something different, then you have a problem. Then you need to build them again. You design them again and bake them again. So making changes to ASICs is very difficult. I was actually, by the way, just last week at an AI startup. They do a lot of embedded AI, and the owner will also be here for a guest lecture in a couple of weeks. That's the company called AI TAT. They're coming sometime, I think, in June. And they do embedded AI. So they build very small chips and they put AI on these, or these chips allow to do AI. And it's something I found super interesting when I was there last week. And it's a startup, and they even do the manufacturing on their own. And they will be here in June because they're desperately looking for new talents. So maybe this is something very interesting for you to see. But still, these are ASICs. And if we want these chips to do something different, we need to redesign them and manufacture them again. And an FPGA is a very generic piece of hardware. So an FPGA is a field programmable gate array. What does field mean in this context? It means with the customer. So the person who buys the FPGA, that's the customer, and that person would program that in the field. So that's what field means in this case. Like you are a computer scientist and you need an FPGA, you're going to buy one. And you can reprogram that in a very interesting way. An FPGA looks internally like this. It's a very generic piece of hardware, and it has lots of flash cells that are interconnected. And how exactly you interconnect them, or which settings you put in these flash cells, so which of these chips communicate and which logic they have, this is something you can set. So you have a very generic piece of hardware that you can customize, and it will do something different for you. The only problem is now, how do I know which flash cells I need to connect how and which logic functions they represent? This would be very low-level work. So instead, what we use is a hardware description language. There are various hardware description languages. One that has become very popular is VHDL, which stands for Very High-Speed Integrated Circuit Hardware Description Language. And if you zoom in, you will see a bit more. Oops. And you see this, it looks a bit like a programming language, right? Looks like, I don't know, C or some variation of this. But it turns out VHDL is probably most important for today. It's not a programming language, it's a hardware description language. So I use VHDL or Verilog as an alternative to not write source code, but rather I use it to define how the hardware would behave. So I'm implementing behavior. And this will not be run on the chip, but rather you will use a tool chain to map what you have described on the exact architecture. So the mapping would eventually lead to you use VHDL to describe how your hardware would perform, and this would be mapped on that specific FPGA. And there are thousands of FPGAs you can buy, so a good tool chain would allow you to work on as many possible FPGAs as there are available. And then you have described how your hardware works, and it's mapped. And then you have your FPGA, and it has input and outputs, and eventually it will do some logic for you that you have described. If the hardware works, it's fine. If it does not work, you just change your hardware description and you map it again. So you don't need to dump the ASIC and build a new one. And this is actually something super cool that has become quite popular probably in the last 25 to 30 years. And FPGAs can be used for lots of different computational tasks, including training neural networks. So what some people are doing now is, or have been doing for the last years is, so you have a GPU. It's still a very generic GPU, like some hardware from NVIDIA, but maybe you build a very custom neural network and you want to train much faster that specific neural network. And a general purpose GPU from NVIDIA may be okay, but not the ultimate solution. So what you can do is, maybe you can use an FPGA and customize it as a piece of hardware to your neural network to do the training much faster. So this is something quite cool. If you have never come across FPGAs, if you ever find some time, we have a lab here and we have FPGAs here. And I think there's even, some professor in one of the degree programs teaching an elective about this. If you ever come across it, take the opportunity. It's a totally different area of computer science than you're in now. But if you build your own hardware, it's a very interesting experience. And these FPGAs, you can always reuse them. You don't need to dump them. So it also keeps costs low. And obviously, your development cycles are very short because you don't need to bake a piece of chip. Rather, you just reset the GPU. And you can use this also for neural networks. So we have looked at the big data architectures. We've seen quite some different stuff. We've seen distributed systems. We've seen MapReduce as an approach to distributed systems where we don't need to worry too much about the parallelization on our own. Rather, it's done for us. We just describe or implement the mapping and reducing functions. We've seen the cap theorem, a fundamental limitation of every distributed system. And we've seen a bit how we can actually speed up big data architectures with regards to training for machine learning problems. Now, we'll come to a different chapter in which we worry about some practical data issues you will come across in the real world. Many of you are doing the AI project with me, so you get real data from the industrial partner. I know one partner has not delivered the data yet, but will hopefully happen very soon. But the other industrial partner has already shared some data. And maybe the students who don't do AI project with me, maybe just raise your hand if there's a, okay? So the ones who are doing it with one of my colleagues, do you also get real data from industry to work on, or do you get some academic data sets, or?
Data-driven exercise.
Okay, so what's the task you're working on then?
It's closing vulnerabilities in chatbots.
Okay.
So this would take like a small chatbot, like 1 to 4 billion parameters, and we try to close all the vulnerabilities like prompt injection, injection, yeah, all of the stuff.
Okay, so closing vulnerabilities in chatbots is one of the other projects. But the students who work on one of the AI projects supervised by me, we get lots of data from the industrial partners, and something you notice is the data looks totally different to academic toy data sets like MNIST or Titanic or whatever. And so data quality is a huge issue, and machine learning eventually is garbage in, garbage out. So we need to discuss data quality. One particular issue in data quality is biases, meaning the data is not representative, and then the model learns that bias and behaves in a biased way. We will see this. And all of this happens a lot in big data sets, but sometimes also in small data sets, because maybe you just have a small data set that is not representative. But among small data sets, some strange other issues can happen. And now what we will look at is we will look at small sample size problems. Maybe you're wondering, why are small sample size problems part of a big data course? Because maybe for some machine learning problem, you overall have a huge data set, but you just have a few samples in there, but each sample is huge. This could happen, for example, with CT images. They're huge, so computed tomography, but maybe you just have a few samples of a patient, so it's still a big data problem, but you just have a few samples, but each sample is huge. And that's why we're also looking at small sample size problems in this course. And I wondered what I should call this chapter. And I said, well, we have some big data problems, small data problems. So let's call it big data, small data, all data. The big data, so we looked at, when we started with this course, where the term big data comes from. We've seen also now for the last probably 2 decades, big data has become extremely popular and has become the dominant research direction in machine learning. And there is a very famous quote or saying in machine learning and big data. It's very important that it does not come from this paper. But this paper here from 2001, it had huge impact on the natural language processing field. What it was called was scaling to very, very large corpora for natural language disambiguation. But something that was very, very large 24 years ago is maybe not that large from today's standards. But this paper is often associated with a statement. This statement is not made in the paper. It was more like a consequence, how people interpreted the paper. And the sentence is something like, it's not who has the best algorithm that wins, it's who has the most data. This is something that is often seen as a consequence from this big data approach in machine learning. Do you agree? Would you say it's true that it's not who has the best algorithm that wins, it's who has the most data? Do you agree, disagree, yes? Okay. Okay. Any agreements or disagreements? Yeah. So one student says he agrees, one said it's a balance. And I agree with that too. So something that was seen in this paper, and it changed the NLP field a lot in that time, was larger data sets lead to better results, and the actual model has impact, but is secondary. But I don't fully agree with these two sentences, because it's not necessarily who has the most data. Because if you just add more and more garbage data, maybe you have the largest data set, but it doesn't get you anywhere. So I would maybe say who has the most representative data, because we want representative data, maybe the cleanest data, but it's still also a question of algorithms, like we've seen now with transformers in the last few years. We have huge data sets, but if you plug them into a hidden Markov model, the approach that was popular before, it won't get you anywhere, but new algorithms perform better. So it's a balanced approach. And that's why I want to discuss this sentence with you, or these two sentences, just to see your opinion. And just having large amounts of data does not help you, because data quality is an issue. There are lots of issues that you can face in data quality in the real world. For example, you have missing values in a table, for example, like not available values. Consistency is a huge issue, especially when it comes to dates. What's the date format you're using in your data set? Is it first the year, then the month, the day? What does this mean? What is this format here? Sorry? Could be the American or the German one. The German one, what would it be? In Germany, we would maybe also see, well, this could be the date, then the month, then the year. But in the US, maybe just the other way around, that it's the month, then the date, and then the year. And this is something you will definitely see in the real world, that when you collect lots of data sources, this is typically not consistent at all. So, and then you wonder, what can I do? How can I make this consistent? Maybe you can filter out some impossible ones, like you would mix or swap date and month, and it's simply just 12 months. So month 30 doesn't exist. But with these ones here, they're ambiguous, because this could be the day or the month, same here. So when you collect data from in some process, make sure you collect the data correctly and you document the format and you follow that format, because it will definitely make someone's lives difficult. Then sometimes the data is not valid, because maybe you're storing an age of a customer, and maybe you're storing negative values in that field. So that would be invalid. Or your data is maybe not accurate anymore. Maybe the data is correct, but just outdated from a long time ago. Or maybe it just doesn't make sense because the customer was born 200 years ago. It's maybe valid, but it just does not really represent anything useful. So there's some error. Do you have more examples for data quality issues that most of you have done an internship in the meantime, so you must have seen lots of data quality issues, I guess. Anyone wants to share some stories, what you have come across? Yeah?
In my case, it was the problem that we have different SAP systems based on which field the company is working in. So it was like 7 or 8 big divisions, and they have different SAP systems. It means that they have different numbers for the supplier of material number, something like that. And then this is the problem to combine it, because it has different numbers in different systems. But when you try to like make a connection between names, the names can be different just because some name has a space between dots, some name has a big letter, and so on.
So one student said in a company they had 7 or 8 SAP systems, and they were not consistent with the identifiers and names. Okay, yes, probably it will be a lot of fun to merge this. Yes?
Was one part that it was these dates utilized. Some of them were given in gigabytes, some of them in megabytes. So it was literally like that, like for example, 80 GB and the next row. 1,000 MB. And when I was doing the report, it was in one.
Okay.
That had to be number, it's only numbers, not without the prefix.
Mm-hmm.
Yeah, starting from there, and also I think gigabytes or megabytes.
Okay, so in short, inconsistent units and stuff that didn't match. Thank you. So we have one student who raised his hand in Zoom. Maybe you want to tell us?
I hope you mean me. Uh, Something I experienced was at BMW. They often have quality checks done with cameras, and for the class which classifies as not okay, they mostly don't have the data for them, so they do it on their own. And this is a big issue, and we had this in your computer vision project class. Yes.
Oh, all right, thank you. I think you also raised your hand.
Problem with the Brazilian government is that because we needed to use it to augment our data. And in Brazil, we needed to get the thing which is called PIB, which is the wage per person in a specific region. But in Brazil, the way that they collect them, it's not state specific, it's region specific. So they made they do a giant square and get each point in that latitude and longitude, let long. And that for that place, there's a specific number. So we needed to get that for São Paulo. That's São Paulo. It's a huge city with a lot of demographic squares. So, but some places, the latitude and longitude were written in a specific way, and some places another way. So it was really messy to deal with that and calculate the area to get the numbers, the exact number.
Okay. So not sure if it was fully through the mic and recorded, but it's a data set from Brazil about the wage in a certain area, but the area was not state specific, but rather just some square or something. And then you have a big city that would have lots of different squares, but probably also not fully overlapping with that. And you would need to figure out for that one city where all the data points come from.
Yeah, I like the area with the latitude and longitude, but the lat long was in different formats.
Yeah.
So it started, and a lot of data was overlapping each other, so we couldn't use it.
Very interesting. Yeah. So the latitude and longitude were in different formats and so forth. Yeah, interesting. One student wrote in the chat that he collected data from multiple machines, but it was never documented and identified which machine is which. Yeah, I've seen this stuff too. Once worked with someone in manufacturing of metal pieces, and they had done lots of data collection in the machines, but they actually never really tracked where the piece goes and at which machine that piece of metal is right now. And also the clocks were not synchronized of the machines. And eventually there was lots of data, but no correlation could be found. So synchronization of machine clocks is another issue that needs to be done. So yeah, thanks for all your insights. All of these are very common issues. And that's why machine learning is really garbage in, garbage out. And what I see is in a lot of courses online and probably a lot of other lectures, in a machine learning course, you would just start here, this is the models like support vector machine and trees, and now run this on your data. And typically the outcome is not very good. What you need to do first is various preliminary steps, and one is that I like to call the exploratory data analysis, a step before training. You would look into your data, explore the data and the quality, try to visualize some of the data, find outliers, and see if this actually makes sense. And if it makes sense, okay. If it doesn't make sense, improve the data quality. You as a data scientist, you will not always be able to assess if all of this makes sense. You need to work together with domain experts. They can tell you if the data makes sense or not, but it's your task to maybe plot and visualize the data and find out some outliers or see if the distribution makes sense. Because something that's also interesting, in a lot of research papers in machine learning, lots of work is spent on improving some machine learning model and customizing it to some specific learning task. And researchers work on this for 6 months, and then they write a paper, and they got maybe 1% better accuracy. Had they just spent maybe 1 week on cleaning the data, they would have got 10% better accuracy. So you see, research is important in building models because we need to have better models, but it's not the only solution. And maybe, so when you work in industry, you won't be much involved in fundamental research. Maybe spend some more time on cleaning your data, and then you get a far better outcome. And the time you're spending on training models, writing code for that is just a minor piece of your work as a data scientist, because you have a lot of preliminary steps and a lot of subsequent steps. But obviously, it's important that you know how to train these models, but your work will be far more. So I have some real-world data here. It's actually from Krones Group, a huge company based close to Regensburg. What they build are bottling lines. So I was in charge of AI at Krones before I got my professorship here and set up a corporate competence center for AI, and we enabled the organization to take advantage of AI. This is some variable from a set of machines. I think these were stretch blow molder machines. So they take a piece of PET and they stretch blow mold a bottle. And what's important is Krones builds special purpose machinery. So each bottling line will be somewhat different because everyone wants different bottles, different beverages. The warehouse looks different. So they have templates, but they always need to customize these machines in some way. So it's special purpose machinery, which typically leads to lots of manual work for engineers, designers, and we advanced AI to automate some of that work, to do also design of machines faster and better. And what I see here is this is from, I think, stretch blow molding machines that stretch blow mold some bottles. And again, it's special purpose machinery. And there is a variable. It's called preform wanddicke Konusende. German and English words mixed. The preform is the piece of PET that goes into the stretch blow molder. And it has some wall thickness somewhere at the end of this. And we see some customers need bigger and smaller preforms for stretch blow molding their bottles. Maybe in some machines, they have very small bottles, in some machines, very large ones. And for this is something that these stretch blow molders were built for. And we see there seems to be a huge peak at around 2.7 millimeters. There are some very small preforms or very thin ones and some super big ones or super thick ones. There seems to be somewhere, the average is around 2.7 and there's the mode, so this peak. When you see such data, you as a data scientist, you don't know if this makes sense because this is just from, a database of all these stretch blow molders that were built in the last few years. There were about 35, 37 with the 2.7 and so forth. You cannot assess if this data is correct or not. You need to bring in domain experts, people from, say, the stretch blow molding business unit, and they can tell you if this data makes sense or if it doesn't make sense, because maybe there was some data processing issue, maybe someone stored this in Excel and recorded it and something went wrong. So such a peak sometimes is true, sometimes it's not true. Maybe it could be a default value. Maybe they just didn't know what to put in their database for a lot of machines, and it just put 2.7 in. Sometimes default values get mixed up with real measurements. In this case, it was actually true. But this is something you would see in an exploratory data analysis, because this was part of a bigger machine learning task for work on stretch blow molding machines, for predicting some of their behavior. And then we saw something else here. This really caught my attention. It's again some velocity within the stretch flow molding machine. It's because in a stretch flow molding machine, you're moving this bottle along, and we had like 540 data from 540 stretch flow molders, and we see the mean is 1.79 meters per second. This is something I can personally imagine and say, well, I've seen how these stretch flow molders run, and the bottles move at maybe 1.5 to 2 meters per second through the machine. Okay. But then we saw there was a maximum value, and actually not just one, but quite a few, of 800 meters per second. And when I presented some AI work also to the top management, I also talked about some of this work to the chairman of the company, who's a very wealthy person, by the way, and his father had established the company 70 years ago. This guy said in my speech, and then I said, Mr. Chairman, what is that? Are you building stretch flow molders that have rocket propulsion? You know, and the chairman was laughing because obviously this is not correct. But where does it come from? And why is the maximum value precisely 800? Any guess what may have happened in here? Yes?
This is like the boundaries of the value that you can put in the system.
Okay, but for some examples, the maximum value was then put in. Yeah, you?
The limit 1.5 meter, and the bottle came in like 1.8 meter, and the other bottle came after it. It senses this as only one bottle, so it keeps measuring and measuring.
Well, the 800, we also didn't know it. And for this, you need, obviously, if you use such data, you will get massive problems in your learning because you will totally bias the learning with this kind of stuff. Well, one person watched a YouTube video and already knows this. It's correct. It's an error code. Error here, 800 meant could not be measured. So this is how the system was set up, the measurement system, because this was run experimentally. And when it couldn't be measured, they put in 800 as a default or as an error code. So mixing numeric measurements with numeric error codes, something you see quite often in industry, because no one, when these systems were built decades ago, no one thought that one day you would need this for machine learning, or that the people who had come up with that idea retired. And for this, you definitely need an EDA to see such stuff, these outliers, and then figure out if they make sense or not. There was also some other variable in the stretch flow molder, again, some speed, which like 140 meters per second, probably also not realistic. But maybe some of these could still theoretically be possible for some very special purpose machines. But you need to talk to the domain experts, and maybe for these extreme values, train a different model, because maybe these extreme values would totally bias your learning. So, and all of this was noticed because of the EDA. Had we just done the machine learning on the data, we would have probably not done our task very well, because we had hundreds of these variables and we had to look into them and improve the data set. Now we're coming to another issue in big data sets, which are biases. The term of bias in machine learning has been used for, or has been in the news for possibly the last 10 years or something, and gets a lot of attention. And we hear about all these models that discriminate, for example, against women, against other people in society based on whatever property. And then there's this claim the machine learning model behaved racist or whatever. But eventually, again, machine learning is garbage in, garbage out. So we are just learning some pattern in the data set. And if the data set is not representative, we have a problem. And this is what bias would actually mean here, that our training set is not representative for the test or production set. Obviously, these sets are different. We always want a different training than the test set. But if their distributions are different, then we have a bias. And this happens in a lot of tasks, not just in machine learning, a lot of statistics tasks, where the data is simply biased. I don't know if you look into, I don't know, books for skin doctors, literature for skin doctors, mainly it's just white skin. What if someone with a different skin color is going to the skin doctor here in Central Europe? Maybe the person is not familiar with recognizing certain diseases, so also a bias. And these biases are obviously then amplified by machine learning models, because if we train them on biased data sets, we're also making biased decisions. But first of all, the term bias means a lot of different stuff in machine learning. It's not always just something that is not representative. The term bias has lots of very different meanings in machine learning. First of all, every machine learning model has an inductive bias. Inductive bias means this is the set of assumptions the learner makes. For example, linear regression means our assumption is we use something linear. While a support vector machine, we have other assumptions that we make, or in a tree, we make assumptions. So all these assumptions that a learner makes is also a form of bias, and this is often called the inductive bias. And we need to make an inductive bias because every model is always, not just in machine learning in general, model is always a simplification of reality. So we need to make some constraints. Sometimes in the literature, bias means that it's a synonym for underfitting. Like variance is sometimes a synonym for overfitting, and so is bias a synonym for underfitting. Again, something totally different than the inductive bias. If you have a hypothesis, something like this, so we make a prediction based on our parameters and the inputs, from X, we have the inputs, X1 up to Xn, and we have our weights, our parameters in the statistical model. Sometimes this y-intercept, W0, which is not multiplied with any of the parameters, just the y-intercept, is sometimes also called a bias. So we see lots of different stuff here means bias. But from now on, when I talk about bias, what I mean is that the distributions of the training set and test set are different. So something different than this one here. And I see, this whole issue of bias in machine learning and bias in AI, there are whole NGOs combating this and are at war with machine learning sometimes when you see this, and they claim that every, AI model would discriminate against someone. I think most of these people who work in this field, in these NGOs, they even don't know from a mathematical perspective what a bias is, and that it may mean lots of other stuff. So this is obviously not an exhaustive list of what bias may mean. It's just what came to me as a most intuitive ones. But from now on, we mean that the distributions of the training set and test set are different. And there are severe consequences from biases, because if we draw conclusions from biased data sets, we have a problem, because the conclusions we make are biased too. And maybe our conclusions don't generalize, maybe we cannot reproduce the experiments. Problem. But this is not just an issue in AI. There has been some arguments that this is a common issue in all research around the world, in every field, not just in AI. And there was once a paper claiming most research published in the world is actually wrong because of biases. But this is a highly contested topic. And in case of discrimination, what can happen is machine learning models, they learn a bias and then discriminate against underrepresented categories. And it turns out that biases in AI are nothing new. It has been an issue in statistics ever since. Nowadays, these predictions of elections, of the outcome, they work overall quite well, but it took a long way to make it there. And there's this very famous example from 1936. It's purely a statistics problem, but we will later come back to machine learning. So in 1936, Roosevelt was running for re-election. He was elected in 32 for the first time and then ran for a second term. Eventually, he had 4 terms, but that's a different story. And his challenger was Alfred Landon, at that time the governor of Kansas from the Republican Party. And there was a very famous magazine at that time, the Literary Digest, a general interest weekly magazine that was very popular in that time. And they had predicted correctly the outcome of the 5 past elections, 1916, 1920, 24, 28, and 32. And they did straw polls. And they wanted to make a prediction in 36 as well. So what they did is they sent out 10 million questionnaires to voters to predict the outcome. And they got back 2.3 million returns, and they predicted that Landon, the governor of Kansas, would win with a major lead. Now, none of you have heard about Alfred Landon before, so probably it didn't work out very well. So something went wrong. This was actually the outcome of the election. So Roosevelt won in nearly every state. So it didn't go very well for Mr. Landon. Yet the Literary Digest was so sure that he would win. This leads to some interesting questions. How could a prediction turn out to be completely wrong, even though there were 2.3 million returns? What do you think? Okay, that could be one thing. They mainly focused maybe on Kansas, and then there was, but he even didn't win Kansas, so didn't go very. His home state didn't work out, so that's a problem. Someone says that 2.3 million were only his supporters. Okay. This is actually partially true, but the cause, we need to come with a better question. How were they able to collect 10 million addresses in that time? Because this was long before computerization. There was lots of manual work, and they made sure they counted the result correctly. This was all triple checked, so that was not the issue. What happened was you need to get 10 million addresses. And what they did was they looked into car registrations and phone directories. But this was, almost 100 years ago. So this represented a much richer part of the population that had a car or a phone. So actually addressed disproportionately rich people, heavily biased sample of the population, and they actually favored Landon, not Roosevelt. So a major bias in the data collection. And it turned out that from these 2.3 million that returned, there was also somehow a bias from them who preferred Landon, so they responded rather than the others. But the major bias was here. The 10 million recipients went totally wrong. And it turned out in the same year, a person called George Gallup was active. And he predicted the outcome of the election very well from 3,000 interviews. He handpicked 3,000 people throughout the country. And with that, he could predict the outcome extremely well. So he made sure that, poor neighborhoods are represented, different parts of the country, rich people, all of this, different ethnic groups, and with 3,000 people, he could predict this super well. It took until the 70s, until this was fully understood what went wrong in 36. One consequence was very clear. The Literary Digest disappeared very quickly. No one wanted to buy that one anymore because they were so wrong. And these predictions, they turned out to be wrong again. For example, in 1948, Truman was running for re-election because, he became president when Roosevelt died. And then a newspaper predicted that Truman would be defeated, also from some statistical analysis. And they were so sure they had already printed the newspaper. And then Truman was re-elected, also because that newspaper picked a heavily biased sample And this happened again in 2016. Newspapers also went ahead printing who they thought had won. So it's still an issue today to some extent. Something that, or what exactly went wrong in 36 was only understood in the 1970s. So then it was understood how that bias was created. So it took actually quite a long time in statistics to be understood. Now, what is a bias? We've said that the two distributions are different. In next week's lecture, we will discuss this together, and we will see from a mathematical perspective what a bias actually is and how we maybe can measure bias, how we can reduce it. But before we stop, and I quickly skip through this, you will have one quick task for next week. There is the MLOps chapter. The MLOps chapter is actually very short because it contains 2 references to very good blogs and surveys of what MLOps is. So MLOps means you not just build your machine learning model, but you put it in production so it runs reliably and consistently and high performance. And this is a very busy or very active field, and I felt that these 2 surveys here, they cover it quite well. I've also given you book recommendations. Take a look at these 2 surveys. The problem is the first one I noticed in the morning has disappeared from towards data science. But you have the URL, so you know the tools to find, like the Internet Archive, where to find this stuff, or you just read the second one. This will give you a little bit of hints about the key issues of MLOps. You will see MLOps again with some of the guest lectures, but also with regards to your seminar presentation, because I sent an update on the weekend that starting in 2 weeks, I think it's April the 23rd, you can pick your seminar topics. So you still have 2 weeks until the portal opens, but some of the seminar topics are from this machine learning design patterns book, and a lot of them actually address machine learning operations. So in order to make an informed choice for your seminar topic, maybe read these 2 references here about MLOps. This could help you to make a better choice. And then next week, we continue with the biases that we've just started and discuss them from a mathematical perspective and look into a few other things. If there are no more questions, we're done for today, and see you next week in a lecture.